So welcome, geologists, and we're going to be taking a look at rock deformation. How is rock deformation different from faulting and mountain building? Well, they're very closely related. And likely if you have mountain building, you're going to have both faulting and folding occur. But deformation is where rocks that were once laid down flat have been changed their shape, much like you see right here in the Canadian Rockies. I took this shot at Waterton, Canada, which is the northern part of Glacier National Park, and you can totally see that these sedimentary rock layers have been bent. That bending happens beneath the Earth's surface, usually many kilometers beneath the Earth's surface, where the rocks can get hotter but not molten, so they become more plastic and Play-Doh-like. I'm making it sound like it's easy to squash and move around. It's not like that. They're still rocks, but they're softer. And so any kind of movement, compression, shearing, or tension, which is the three types of stress we're going to be learning about shortly, can alter these rocks if they have enough heat applied to them. So let's define a couple of important terms from your textbook. Stress and strain. Stress is the force that gets applied to some type of a rock or to the Earth's crust. So that's kind of how you may feel when you have an assignment done. You got a lot of stress on you. You may feel like you have tension, which would be pulled apart at the seams. You may be everything's crashing in on you. That would be compression. And sometimes it feels like things are slipping right by you side by side. That's shearing. Well, this happens in rocks too, and depending on the type of stress that's applied to a rock, the end result of the deformation and or faulting will look unique. So the strain is the end result. This is what happens to the rock that's the permanent deformation. So let me give you an example from a way you'll probably associate with. Let's say that you have not gone and run for a very long time, if at all. And then one day you get the brilliant idea that you're going to go run 5 miles and you haven't done any stretching, you haven't done any conditioning. How might you feel the next day? And you're like, I'm going to be very sore if I can walk. And that's probably true. Now, if you run every day, if you're trained for that type of event, the stress would be very minimal to your body. But if you just started that outright, you would have probably some torn muscles, at least strained muscles. Now, the good news is most of your muscles will heal and recover. Sometimes in the rock situation, we apply so much stress that the strain is permanent. And so that permanent look has made the rock change its shape, which is ultimately rock deformation. So let's be very clear on the 3 types of stress that are occurring to rocks. When you get compression, which is this one right here, you got things that are smashing together. So some kind of compression happens like this. So this is very important because whenever you squish things together, you can create, test question, folds, reverse, and thrust faults. Very specific. It creates all types of folds, reverse and thrust faults. We'll be learning about the faults a little later. If you've got tension is where you get a rift or an MOR where the crust pulls apart. So it'd be like pulling a rubber band until it snaps. Shearing is where you get like scissors where things move side by side. So there's no compression, there's no pulling apart. There's simply that shearing mechanism like scissors that are cutting something. When rock folds are formed, they're created because of 4 major factors. The amount of stress that's applied to the rock, so that would be tension, compression, and or shearing. Now, FYI, you're not going to have tension and compression happening at the same time, but you certainly could have tension and shearing happening at the same time, or compression and shearing happening at the same time. Now, the temperature of the rock is a huge component of how deformation occurs and the significance of that deformation. The pressure that the rock is under, meaning the amount of weight that's above it, plays a huge role in how easy it is to deform rocks. Obviously, the actual composition of the rock is important in understanding how deformation can occur. So rocks are very brittle at the surface, meaning they seem like they're rock solid, right? But they're very hard to mend, bend, or be pliable. But you get them inside the earth where they can warm up, and those rock layers have pressure on top of them, which add friction to the molecules and atoms inside. It can become more ductile. Ductile would be like a hard block of clay that's been heated up, if you've ever worked with molding clay, and then it's able to be bent and shaped into the shapes that you want it for art. Well, if we can do that to rocks, we can make some very interesting shapes. So keep in mind that there is a difference between having deformation and reaching the fracture state. If I reach the fracture state in a rock, that means I've exceeded its ductile formation. So if you get to a point where your strain is irreversible and folds form, the rock has permanently changed its shape, but it's not broken. If you end up to the point where you get a fracture in the rock, where the rocks have actually moved, meaning the rock blocks, then you have created what's called a fault. There's an interim step from having a fold into a fault called a joint. A joint is where you have a fracture in a rock where no movement has occurred. So obviously temperature is one of the most important factors that can drive creating this under the surface. I can't underscore enough the importance of you realizing that this kind of bending and folding of rocks cannot happen up here. It's got to happen subsurface. Confining pressure also is a huge component in this, because if you have low confining pressure, you're not going to have very good rocks to be malleable. They'll be very brittle, so they'll break. But if you have higher pressure, that means more friction on top of those rocks. It actually adds a heat component and allows those rocks to be more malleable. Geothermal gradient, you learned about in metamorphic rocks. It represents the temperature change that happens to a rock as it goes down 1 kilometer in depth through the subsurface until it reaches a pretty much stable temperature change in the mantle. That's 25 degrees for every kilometer. Well, it also changes in pressure. So this is a new test question for geothermal gradient. 5,000 pounds per square inch increases every time that you go down a kilometer. That's an incredible amount of pressure. So you add that with the temperature, you can do some really interesting things to rocks. So let's talk about how we measure the orientation of rocks and why we would even care. Orientation of rocks is measured by using tools called strike and dip. The dip is the easy part, the strike is the harder of the two. Both are critically important for interpreting where rock layers are. So most folks that are not geology majors look at this and go, why would I ever care about strike and dip? Well, let's just say that we know there's a rock-bearing layer of material. Let's say that if we could follow this layer right here all the way down, maybe a mile under the surface, and we know that it bears gold. Wouldn't you want to be able to follow that path all the way until that rock pinches out? So you're going to need to know the compass direction in which that rock layer is laid down. Second of all, you're going to want to know how to dig and at what angle, because you don't want to be digging this way and miss your rock layer that has gold if this one has none in it. So that's where the dip comes into play. So you really can't get the gist of rocks until you see it from an aerial perspective, like from a plane looking down. Because when you start to look at regional perspective of rocks, you begin to get it that rocks are large scale, that they're not isolated to one area, like this outcrop right here. When we see rock layers or rock strata that have been inclined, we know that they've been changed from their original position from crustal deformation. So that could be from uplift of a mountain, that could be from another type of geologic process like an earthquake. There's a number of causes that could occur. But nevertheless, we use strike and dip in order to interpret the amount of change from its original position at 0 degrees. So to define the terms for test purposes, strike is the compass direction that measures an imaginary horizontal line that shows the compass north to south or northwest to southeast type direction, so you can follow the rock layer underground and at the surface. Dip, however, is a little different. So I'm going to tell you of the two. Strike is much harder to do on a Brunton compass than dip. So dip is the stuff that is measured. It's the inclination, to be exact, the angle between that strike line and its inclined plane. So basically it's how much has it been pushed up or down. So we're looking at angle here. Dip is a grade, if that helps you understand. If you ever come to a road that has a percent grade, that would be a good example of dip. So everywhere has usually slight amount of dip. Very few places have just literally zero dip, but they could, I guess, prospectively. But nevertheless, most rocks have been changed from their original position in some shape, fashion, or form. And the dip is not consistent in an area usually. It varies. So remember, the strike is going to be this line right here, if you see in your books and so forth, or a diagram, and you see this line is measuring a north-south direction. The dip, this is little hatcher mark right here, indicates the direction that the rock layer is dipping. So this is, if the little hatcher mark points this way to the left, that tells me it's dipping to the left at a 30 degrees, because this number tells you what the dip is. If the hatcher mark was on the right side, that would tell me that it would be going downhill this way. So the way you kind of look at it is almost like if this line would represent the top of a slide. And you're going to make a decision which way you're going to slide down, right? Well, there's stairs on this side coming up to the top. This hatcher mark is what makes you slide down the hill. And then that way you can figure out how it's working. Because not all lines are going to, strike lines are going to be straight up and down. You might have a feature that's circular, and you would have strike lines all the way around it. I'll demonstrate that shortly. So all we're looking at strike and dip is the angle of these beds subsurface. So you can see here's what would be at a road outcrop. And see how it continues under the Earth's surface, even under this water? Well, we're interested in the angle by which we could find that rock layer. Again, maybe it contained gold. And second of all, we're very interested in the angle that it's been changed from its original position, which would be dip. For testing purposes, all you need to know are definitions for strike and dip. This is the instrumentation by which we use and find a strike and dip. There's a variety of different types of Brunton compasses, and before you decide to go out and buy one, you should check out with us, which is probably the best fit and the easiest to use. But nevertheless, these simply measure the dip and the strike of a rock layer, and it is very important in geology to do this because it helps out for mapping and putting precise locations to where we find things. Let me give you one more example. You're at a dinosaur dig and somebody finds the fossil of the year. They're going to want to know where that T-Rex skull is. So you immediately take a strike and a dip measurement. And you would do that for every bone that's found at your site, so you can accurately describe the dip of the land and the lay of the land. That's important to publishing that work. It's important to interpreting how the bones were deposited in that area. This is an animation that's actually from Exploring Earth to show you how continental accretion occurs. So this would be like an island arc, similar to Hawaii, but instead of smashing in somewhere else, it would be smashing into our west coast. And this is exactly how we have gotten bigger land masses around all continents around the world, certainly around North America. So as it gets pushed in by an MOR somewhere over here, a mid-oceanic ridge, that pushes this plate into the adjacent plate. So you have to realize this thing's not going to move without a plate boundary over here that's separating it from its adjacent plate, which would be this ocean plate. So it's going to split there at a mid-oceanic ridge and come in and get squashed. So what will end up happening is you can see some of this continues to go down and is subducted. The rest of it ends up gluing onto the continent. That's called accretion. So accretion is the process by which we add new continental material and grow the edge of a continent simply because of this process of a mid-oceanic ridge separating this ocean plate from this part of it and sending the terrain, which we would call an exotic terrain, and it squashes into a pre-existing terrain. So a terrain is simply a group of rocks that share a similar history. Obviously, there's going to be faults that separate each of these areas, and that's one way you can tell that you're in a different moraine. So the next part of deformation is folded rocks. Folded rocks are when rocks get compressed. This can never happen with tension. It will not happen with shearing, although shearing can make a special type of change to a pre-existing fold that I'll show you shortly. But folded rock layers always happen from compression. So when rocks get compressed under the ground, they can make funny shapes like this. Well, that's an extreme amount of compression there. So you have to ask yourself, what in the world could cause something like that? So let me kind of unfold those rocks for you and think about, all right, this was probably flat ocean bed layers that were at the bottom of the ocean, and as that island arc came in that I showed you from accretion, it smushed up some of those rocks against the continent, and voila, there you go. That's what folds look like. So there are three basic types that you need to know. The Monic Line is the easiest to recognize, I think, simply because it bends in just one direction. Mono means one, and it has a bend in one direction like you see right here. One of the most famous monoclines in North America is the Grand Monic Line. That is where a big system has folded rocks and even created some faulting in the Grand Canyon. But in this area, it's just created a fold. And you can see how it's bending in one direction. Now, we've lost some of these rocks due to differential weathering and erosion, but this is still definitely intact, bending in just one direction. If it continued to bend and made an arch like this, it would be a different type of fold. So here's the Grand Monic Line. You can see it just kind of bends and folds in one direction, so you only get folding that one way. My Anticlines are my personal favorite. I think they look like rainbows and arches. So A for arch, that's easy to remember. And this is where you get an upward bend in rocks. Your oldest rocks are going to be down here in the core. Your youngest are still at the top. Because remember, you had flat rock layers and you've just pushed them up. So an Anticline, it's very easy to recognize because they make big giant arching folds. Clearly an anticline, but you might go, what's up with this thing over here? Well, it's the other side, which is where the rocks make a dip downward, which would be a syncline. We'll learn about those in a minute. Here's an anticline in the Smoky Mountain Range. You can see clearly that these rocks have been bent and folded as an arch. So synclines are the opposite of an anticline. They dip downward like this one does right here. They're still caused by compression, and oftentimes you will find synclines and anticlines married up together side by side with complex folding. So the youngest rock, it's going to be in its core right here because it was at top. The oldest rock should be at the very base down here. When you see that bending arch down at the bottom, you know that, and it looks like it's just sinking down, a sinking arch, then you know that you have a syncline. I have traveled a lot, and I've seen this spray painted on a number of roadside outcrops with synclines, so I guess it's geology humor. But people will sometimes spray paint faces on them because it looks like a big smiley face. So that's one of the ways I remember a syncline, S for smiley. And synclines are just a simple type of fold where you have a dip downwards instead of the arch upwards. So which one is this? Is this an anticline, syncline, or monocline? And the answer is definitely synclines. If you put a little eyes here and here, notice it's smiling back at you. It almost already is right here. Your little eyes, your mouth. What you got here? Anticline, syncline, or monocline? Or monocline? Anticline, syncline, or monocline? And obviously it's bending in one direction, so the answer would be monocline. What's that right there? This is along I-35 as you go through Ardmore, Oklahoma. This is the Arbuckle Mountains, what's left of them anyway, and you can see a big arch downward. So if you put eyes here and a little smiley face, you would see that that is definitely a syncline. What you have here? Well, you're like, we got more than one thing, and if you said that, you're right. So what's this feature called right here? That would be the arch or the anticline, right? And here's your downward arch, so that would be the syncline. This is a good example of what happens when you see complex folding. So this is what happens when folds happen together. You get very complex folding. If I see this, then I know that there was a very big story about how the plates were merged together and how they were folded. So these complex folds can make some really strange shapes like you see here. And bottom line is these are all complex folds. We're not going to go over all of them. We're really going to focus on recumbent folds, which is a form of overturned folds. But I just kind of wanted to show you some weird things. Like here's a chevron fold. So most of them have different angles when you get a complex fold on one side of the fold versus the other. Can you see how this has a higher dip than this does? Right? It's like they've been harder compressed on one side versus the other. So what that basically indicates to me was that a plate smashed in faster on one side when it smashed into these rocks, causing one side to be buckled up more than the other. So complex fold situations are just clues, just one more clue for a geologist to help piece together the story, what happened in geologic past. So overturned folds are a situation for complex folds where both of the fold limbs dip in the same direction and the fold has just been moved from straight up and down like synclines and anticlines, and they just get turned over on their side. So when this happens, they've just been rotated 90 degrees from their original point. So this one that you see right here would have been more like this shape right here. And what happened was it just got knocked over and put on its side right there. Recumbent folds are actually a complex fold situation where the deformation is so extreme that the axial planes have become horizontal, almost like you folded sheets for your bed. This creates a special type of overturned fold. So it definitely is an overturned fold, but it's called a recumbent fold. So this extreme pressure and stress that's applied to this rock during compression also experiences shearing in most cases, and the shearing allows for the folds to almost be nicely folded in half because the shearing actually allows the rock to kind of compress more together. So usually you'll get faults in these areas because the rock just cannot stand the incredible amount of stress and strain that it's under, and ultimately it buckles and makes faults. But this is a great example of a recumbent fold. Here's another recumbent fold right here. You can see that's radical folding. So wherever you see this, you know there's usually been a major mountain building event from a plate collision, and that's what it should tell you. There's something called a plunging fold. Plunging folds really are more advanced in this class in my book, but they refer to how a fold looks when they appear to dive or plunge underneath the Earth's surface at adjacent rocks. Well, what happens is the layers dip away from the fold axis in plunging anticlines, and they dip towards the fold axis when you've got a syncline that's plunging. So what does plunging really mean? Plunging means you've got a fold that dips between 10 degrees to 80 degrees. That's a test question. Most folds have some degree of plunging. If they're less than 10 degrees, they're not plunging folds. However, if you get a fold that's between 81 and 90 degrees, you'll have something that looks like this. Well, this is insane, right? What could cause something like this vertical fold? That's radical compression. So vertical folds, if you see them, you've got to imagine that you had crustal deformation so extreme and probably the rate of movement very fast that it did have no chance for these rocks except to be completely smashed shut. So it'd be like a notebook that's open and you shut it. That's how extreme this type of folding can be. So again, for test purposes, we're looking at the degrees. I'm not asking you to recognize plunging folds in the field. That's a little higher up in terms of years as a geologist. There's still a few more things that we need to learn about for deformation. Joints, folds, domes, and basins. So once we learned about folds, let's focus on joints, basins, and domes. Well, joints are the first thing I want to look at, and this is our field course, and Russ and I are teaching field course people about these things right here, the cracks coming down Checkerboard Mesa in Zion National Park. So Checkerboard Mesa is the result of frost wedging, where you get, we're high enough in elevation here that the groundwater or surface water, let's say it's rained or there's groundwater in the sand and the stone, and there definitely is, It oozes out, and at night it gets pretty cold, especially during the winter, and it expands and shatters, and it will create joints. There's been no faulting to actually move the joints yet. So a joint by definition is where a fracture occurs where there's no movement yet. Doesn't mean there won't be in the future. Joints are often associated with some type of a folding event. You've also learned about these columnar jointing, if you recall, and columnar jointing is still a joint where there's been no movement yet, but there could be in the future. So here's some more columnar joints, and basically joints is a planar fracture that's formed from a rock as a result of some specific type of stress. So that stress could be shearing, it could be compression, it could be tension, but they're distinctively different because, from a fault anyway, because there's been no movement of the rock blocks relative to one another. As soon as a joint does that, it graduates from joint status to fault status. So there's two more rock deformation structures we need to learn about: domes and basins. So domes would be features like the superdome, right? Where you've got an upward layer of rocks that actually comes up and makes a shape like this. You know, it's a dome. So the rock layers in a dome dip away from the center, with all the rocks getting old from the outside in. So it's not an anticline. Don't think of it as an anticline. All the folded rock layers dip outward from a central point as opposed to a single line like it does in an anticline. So this is actually a full relief feature on the ground. These are easy to recognize. Now the way we can do that is by looking for strike marks and dip marks, hatcher marks on a map. So basins are opposite of domes because the highest elevation point is around the edges. That's your youngest strata, and then it dips down towards the middle, which would be the bottom. It's like a big gigantic pool. And so this is often going to hold water. Basins don't always have to, but they certainly can because they dip inwards like a big cavity in the ground. So that's important to us geologically because that could contain things like oil and gas. So how do you know if this is a basin or a dome? You look at the strike and the dip marks. So remember I told you strike lines could be in different directions. So this is a strike this direction. Here's one here. Here's one here. Here's one here, 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 and here. So the important thing is to look at this dip mark here. Since the dip is this way, remember this would be the top of the slide, and whichever way the dip mark's pointing is the way you would slide. So you would be sliding down the hill this way into the middle on all of these cases. Now, if the hatcher marks are on the opposite side, you'd be coming down this way, and this would be a dome. So in this case, on this particular diagram right here, I clearly have a cavity because the dip marks are pointing towards the basin or the bottom part of it. So you'd be going downhill as opposed to uphill. So domes and basins are simply just features that can be denoted on a map by simply using strike and dip marks. Important for you to know in the field before you go somewhere if you're going to be traveling in a dome or a basin situation. So let's take a break and we'll come back and learn about major faults around the world, and we'll learn about the various different types of faults and apply that to rock deformation. I'll see you in a little bit. Bye.